Well, ho Aeon Melon. Good evening. My name's Joe. People call me Mr. Melon. It's a pleasure to meet you. Yet again, on this evening, I decided to do something a little different. We're going to go ahead and do this video at night. You know, a lot of things happen at night, or in the dark, I should say. Think about it this way. This paper, we're going to go over the origin of inertia. Now, at the scales where inertia first starts to have its effect on matter, you don't see light down there. The scale is 10 to the negative 19 meters. And I know that doesn't really mean much, me just saying out some numbers or whatever. But you're so small that you're inside the lattice. If you were looking around, you wouldn't actually see the light, you would feel it. It would just be wiggling around you. So that being said, it's definitely a different perspective on reality than what we experience at the macro scale. A typical a typical photon of visible light has a wavelength of about 500 nanometers. So that's 10 to the negative 9 meters. If you are scaled down to the size of a vacuum grain, 10 to the negative 19 meters, a single wave of light is 10 billion times larger than you and the grains around you. So think about that. That is a huge scale difference. It's like the ocean swell in the dark. You know, if you were out floating in the middle of the ocean, a wave comes by, you're treading water on a pitch black night. A massive tidal swell rolls through. You don't actually see the wave rushing at you. Instead, you just feel the water lift you up, stretch you a little bit forward, and then smoothly drop you back down. It's the same effect at this scale where inertia first takes hold. You know, if you were watching these individual grains, they wouldn't just shoot past your face. They would just be unfathomably large rhythmic waves of tension and torsion that would just wash over the area. Millions of grains would suddenly stretch horizontally, twist vertically, and then snap perfectly back into their original geometric alignment, leaving a net zero volume displaced. So it's just the lattice itself moving. I did want to illuminate the whole process that I had taken to get this paper to where we're going. And so the progression of this paper, it did not happen overnight. You know, it's been quite a bit of work and me trying to prove it wrong and not being able to do it successfully. So think of it this way. The first paper that I initially drafted in 2021, I developed the space energy cutoff, the tensor cutoff. Pretty much that space has a limit of what it can hold per volume. I figured out that the geometry of the standard model was string theory. So we've really kind of had it. They just haven't been looking at the math correctly. And I understood that the volumetric expansion is what really affects the curvature of space itself. So those principles that I first developed were the foundation by which the rest of my paper ended up developing. So the principles that I ended up developing over the course of developing this paper is the quantum thermodynamics. It explains what entropy is ultimately. The causal hydrodynamics, the fluid dynamics of moving through the lattice itself. That became apparent after I was able to get the whole picture and then find and dig into exactly what it was showing. The nature of time, that came about with this as well. how does time work? So my initial paper, which I don't have linked on here, really simple. I might end up putting it in this link for this video here on Google Docs, but it's really simple, and it did not have all the math and all the required, finalization done to it to actually support explaining all of the known forces as it does. So the first two steps that were mandatory in this mathematical and logical exercise was, first off, I had to have the geometry prerequisite for thermodynamics. I had to, my paper initially stated that space is finite, it's quantized, it's made of bits of energy or bits of space moving around. In thermodynamics, you studied the transfer and entropy of a system. The rest mass of a particle is defined as the thermodynamic cost of displacing the vacuum's objective geometry. You can't formulate that entropic cost without understanding that there actually was a physical geometric volume being actively displaced. So without me coming to those first realizations, I would not have been able to take the next steps. It just wouldn't have been possible. I wouldn't have had the materials. Next, I had proposed that the standard model particles have specific objective geometries. Hydrodynamics dictates how a fluid responds to an object moving through it. I can't determine the Vacuum Reynolds Number or define flow regimes without first knowing the physical shape and orientation of the object penetrating the fluid. The Finslerian angle of attack, which I'll have that video posted up here shortly after this one, but it's strictly required. It was strictly required in order I needed to have those geometric configurations at first in order to be able to determine the angle of attack was actually relevant and important, and where to find that information in string theory. So I had to build the board to outline the shapes and to figure out what exactly was moving and why we're seeing what it is that we're seeing. So it's been an experience, indeed. And hopefully, and at one of the later videos that I'm going to end up doing, we're going to get into the applied physics of it. What can it actually do? Because what good is a bunch of information if it's not going to do anything? If it's going to make people's lives worse or harder? That makes no sense. So we're not going to do all that. All right. First up, going back to the origin of inertia. Now, to understand why rotating objects resist change in their spin, moving beyond the classical idea of mass and to understand it as fluid drag within the geometry of space itself. That's what we're going to try to cover on this. Now, in classical mechanics, the moment of inertia is treated as a static property of mass distribution. The standard math formula is typically written as I sum mr squared, which means that the resistance to the spinning depends on the mass and how far that mass is from the center. Real world translation. Think of an ice skater. When they, a lot of the physics videos that I ended up watching, they like to use the analogy of a figure skater spinning on ice. They tuck their arms in, they start spinning real rapidly. Well, when they have their arms out, there is a reason why they produce more drag, and why when they narrow down their angle of attack and their size, that they spin up. So when they throw their arms out, increasing their radius, they slow down. Classical physics says that happens because mass further from the center is harder to move, but it never explains why the universe cares where the mass is located. So that analogy, it bridges perfectly the classic and everyday observation with the heavy hydrodynamics of QSM. When they put their arms out, they're making a bigger cross section in space that is displacing more space volume. That's in part because of the moment of inertia. That's what increases their spin. They decrease that overall volume. The mass is still the same, and they speed up. All right. So the quantum space mechanism, ultimately, what I came to realize was that space is not an empty void. All right. It is a highly structured six-dimensional fluid. Therefore, spinning an object is not just moving mass through emptiness. It is actively fighting the angular geometric resistance of the vacuum grains. So it's like for instance, think of it this way. Trying to spin a whisk in a bowl of thick batter. Okay, the resistance you feel in your hand isn't coming from the whisk itself. It's coming from the batter fighting against the whisk's movement. In QSM, inertia is just the vacuum of space fighting back as you try to alter its shape. The math behind the stirring. Let's look at the true formula for the rotational inertia, the entropic moment of inertia. So here's the actual equation. All right, I'm going to show this to you real quick. Let me shine a little light on it. Let me see. Actually, you guys can see that pretty well. That's great. That's the actual equation. All right. So what that means is we can calculate a lot easier how things move through space. That's going to become important later. So breaking down the translation on this, the tangential velocity, further out the spinning disk you go, the faster that point is moving. Now the Reynolds scaling, because the outer edge is moving faster, it cuts through the vacuum lattice harder, generating a higher local Reynolds number. The thermodynamic cost represents the actual energy tax required to displace the vacuum's geometric quanta. Why is R squared still there? Well, the mass concentrated at the rim pushes harder against the fluid, creating a larger geometric wake that incurs a higher thermodynamic update cost from the vacuum. Ultimately, when we end up being able to calculate that better, we can make materials that can move through it better. We can have engines that can take that inertia into account and be more efficient. So, in my paperwork on page 23 and 24, and by the way, the moment of inertia, this is the starting paper in there. So, it's right near the beginning. But pages 23 and 24, sections 8.2, how does the math actually translate into what we observe in telescopes or particle accelerators? There's actual evidence of this kind of an interaction taking place, and they don't exactly have a way to understand that. So I'm going to try to help them out a little bit with this. But the blue stragglers, when stars rapidly rotate, they create a massive swirling vortex drag. This acts like a centripetal restoring force, holding the star together against extreme dispersion. This perfectly explains the anomalous stability of the blue straggler stars, which survive longer in low-density space environments exactly because of their laminar surface frame when it's preserved in the ambient vacuum turbulence and when that turbulence is low. So they've seen these stars that they didn't think should exist, and they didn't really have a mechanism for it. Now we do. The relativistic fireballs. Okay, so they were smashing particles together in CERN, creating high-energy plasma fireballs. Classic hydrodynamics says that those fireballs should fall apart almost instantly due to turbulent dissipation. They didn't see that. It didn't actually happen. There was a delay there. They couldn't figure out why. Under QSM, their velocity, as their velocity nears the speed of light, the vacuum becomes a superfluid, and the effective viscosity drops to zero, allowing them to maintain coherence far longer than what we're accounting for. So they've already seen this moment of inertia and this work in action. That being said, I appreciate you guys watching my videos. I'm going to get on to some much better topics where I'm not just sitting here reading off a clipboard or going over papers that are pretty freaking boring. And, yeah, they're important, of course. They are going to help people understand the nature of the universe they live in and how best to utilize that in the future. But that being said, it is still technically pretty boring stuff. So, that being said, it is the age to come, and I'll be keeping you guys in my thoughts and prayers. And may you have a blessed night, and may peace be with you. Take care. I'll see you later.